So today's lesson is called Introduction to Vectors. Okay, before I begin, so I can know what speed to go, please raise your hand if you've already taken grade 12 physics. Raise your hand if you've done grade 12 physics. Okay, good. Please raise your hand if you are currently taking grade 12 physics. Please raise your hand if you're currently taking grade 11 physics. Please raise your hand if you have not taken grade 11 physics. For those three people that have just raised their hand, I'm going to go through this as slowly as I can, but please realize that as I'm going this slowly, the rest of the class is yawning at me and they're thinking, hurry up, Sadler. That's what they're thinking, okay? So this will be review for the people that are in physics today. But for the people that are not, I'll be as clear as I can. So we're going to say a scalar. I didn't mean to say it like that, I'm sorry. Too bad job. A scalar is a quantity that describes only magnitude. Examples of this are 58 kilograms, 200 kilometers, and 180 miles per hour. Those are all called scalar quantities. A scalar quantity is something that just has a length, but without a direction. Okay, so if I say I have to travel 200 kilometers this weekend, wow, that's awesome. Okay, it could be anywhere. It could be straight up in the air, it could be down, it could be out this way, it could be east, west, whatever, okay? But it's just a scalar, again, it doesn't have a direction. Okay, we're going to say a vector has both magnitude and direction. Examples of this are 300 kilometers north 30 degrees east, 180 miles per hour south, and 20 newtons down. Okay. If you've been in physics, you've seen all these things. If you've been in my grade 10 and 11 math classes, we've also seen all of those things as well too, or at least with north 30 degrees east. Okay, you've seen those before. Remember those Spider-Man questions? Like you're rotating this way and then you're what? Those, remember those ones? You're gonna hate this course if you don't like that. Okay, because that's what this is. Okay, so the difference is for all these, they have a direction to them. Right? That's the only difference between scalar and vector. A true bearing begins at north and rotates clockwise. And Mr. Walter's a big fan of this. If you took his grade 11 course for trig, he loves true bearings. We'd say the angle is 190 degrees. Okay, right? That's what he would use. Okay, he loves those sort of ones. I'm more a fan of the second one, but you're required by law to teach both of them to you. So the second one is called a quadrant bearing. Is compass measurement. And I'll do an example of both here in a second. So compass measurement would be like north 30 degrees east, south 11 degrees west, stuff like that. That's compass measurement. They both can be the same one. Okay. It's coming back for most people, I think. Even Harry, you remember doing this stuff in grade 11? If you don't, you guys do this at all in the assumptions, right? There's no function. Okay. So here we go, example 1. It's going to say, sketch the following vectors. All right, A. please note this does not have to be to scale. Okay, for some reason there are people that don't want to see a 20-kilometer vector. Okay, that will take a long time. All right. So let's start with the direction for this. Somebody tell me so I got our. It is. I'm gonna need you to take over for a second. Can you show them how to do a 190-degree vector? You recall? I'm not sure.
Okay. So for these quadrant bearings, you start at the north section up here, and you go around until you go 190 degrees.
There's no true bearing.
Is it?
True bearing is starting
Sure?
Yeah.
I don't know.
I set them up over there.
No, it shows that you start at the north and then
That's
you
what
go.
I'm saying. If it's a quadrant bearing, wouldn't that be a true bearing?
This is true bearing, yes. This is true.
Okay.
Oh, okay.
Well, for this one then, you go to like somewhere around there, like that.
Yeah, this is the reason why trig is confusing. Okay, because if you think back to the unit circle, where does the unit circle 0 degree start at? It starts here. Which way does it rotate? Yeah, the other way. Okay, that's why trig is confusing. Okay, so quadrant is the way that true bearing starts straight north. And the reason for that is because when you look at you can always rotate yourself to north if you're on the sea or whatever like that. That's where you're starting at. Now hold on, before Michael continues, he made an error, I assume, for the class in this result here. What did Michael forget to do here? Two things. North is okay, I don't care about that. Sorry? Is that? That's fine too, I don't care, well, I probably do.
Well, it's not continuing there.
Just wait, Okay, I'm gonna put it out at the end here. What else did Michael forget? He's got two things here. 20 kilometers, you gotta put on this. Okay, do that to make sure the class is aware. Okay, other thing you should put on there. If I'm looking at that as a math teacher, I have no idea what that is. What else should I put on there? Yeah, okay, the vector's okay. The vector would put the arrow on the end. You should probably put either 10 degrees here, there, or go the whole thing as 190, right? So either go 190. So 10 degrees either from south going west 10 degrees, but you gotta make sure that you label that in there. So that's like what the dimensions are in there, okay? Because if you don't put that into that arrow, it can anything, right? You need like, right? So make sure that unit's going there. Sorry, my those are out there. Okay, this next is 18 kilometers north, 30 degrees west, and I bet your bottom dollar Michael will knock this one out of the park now.
Oh, that's one is the quadrant one, so we sort of sketch like that. So then we know up here's north, okay, over here's west. So those are the two that I put right there. So then we know it's between these two, so we just do a line. It's north 30 degrees west, so we put 30 degrees right there. And we put 18 kilometers right there.
Okay, great. Now the thing is that always gets people when I first show this to them in grade 10 or 11 or like whenever we start doing this one, the north 30 degrees west, they have a hard time setting up. You guys are all calculating, so I'm assuming you get this no problem. But you're still, yes, that's it. If you start north is your starting point, then you're going to rotate from that point. Okay, right? So north 30 degrees west. What would be an equivalent angle to north 30 degrees west? Good? 30 degrees? Yes. What else? West 60. West 60 north of north as well, too. Okay, 30, I like. Also, if you want to go crazy, I can call it negative 30, if you really want to go crazy. Okay, right? But let's not get that crazy today. Okay. Okay, for those, did most of you understand what I just said there? I hope so. Okay, good. All right, here we go. Equivalent vectors. Two vectors are equivalents. If they have the same magnitude and direction. They are opposite if they are equal in magnitude, opposite direction. And we'll deal a lot with equal and opposite vectors in this course. And we'll get to vector proofs coming up. Opposite indirect. Whoops. Thank you. Equal in magnitude, equal in magnitude and opposite in direction. Okay. So again, if you think of forces, which we're going to get into, okay, since I'm the strongest person in this room, okay, right, if I were to pull on Matt, and he were to pull back with the same force, it'd be the same force, but no, I'm not going to do this to Matt, though, okay? If we were to pull him with the same force, and he pulls back on the opposite force, the idea is the magnitudes would be the same, we'd both be pulling with an infinite amount of force, but he's pulling with that direction, I'm pulling this direction, so there wouldn't be any motion. Okay, that's the idea. Okay, right, so that's what opposite are. There's no, they cancel each other out, and we'll get to that here in a little bit. Okay, and that's what, for those that have taken physics before, you know, free body diagrams and all that, you know, an object in rest stays in rest, and you know, for no net force and all that stuff. Does that all sound familiar to people? Because that's what we're getting into very, very soon. If you didn't take physics, don't worry. I'll all be on clear. Okay, so here we go. Example 2. Okay, this is a parallelogram. Sorry. Okay, so letter A is going to say list a vector equivalent and opposite AB. Okay, so let's look at vector AB. I need something that is equivalent to it. Can someone be brave and tell me what equivalent means again? Go ahead. Same magnitude and direction. Now, even though my diagram is poor, and I apologize for that, what does a parallelogram mean? Yeah, two sets of parallel lines is what it is, right? Okay. So let's look at AB. What vector would have the same magnitude as that? CD. Not DC and CD both do, okay? So DC, but we're with nomenclature here. AB means going from A to B. So which one would be equivalent to AB? DC, okay? So we're going to say here then AB is equal to DC. Right, so this is how you'd say equivalent. Okay, so everyone see that? It's not equal to DC because DC would be pointing in the opposite direction. That leads me nicely into our next statement. What is AB opposite to? Right, so we're going to say AB equals negative CD. Now here is a trick. It's not a trick, there are no tricks in math class. What's another vector that AB is opposite to? BA, good, right? Because the same thing, if you take this, going back the opposite direction, you're going to get the same thing. I'm sure if your physics teacher probably tortured you with these sort of things, because they talk about that you run all over the class, but you end up in the same spots, there's no displacement, so you really haven't done anything. Does your teacher tell you that in physics? No? I'm sure they do, okay? They like to do that sort of thing, right? That your speed is this, but your velocity is, they make a big, huge distance, right? For that, and that's the idea here for this, okay? AB is opposite BA. We're good? Okay. Just for fun. List a vector that is equivalent and opposite to CB. Okay, equivalent and opposite to CB. This should be quick and painless. stop the video and let you guys do this. Like you're gonna do National Red tomorrow on the board. You can take this.